Our fifth lecture is about metapopulation epidemic models, which is one way to evaluate the spatial spread of infectious diseases. Before I want me to go on, first, what are we going to look at? And so I should make myself move. The first aspect we're going to look at is how you formulate metapopulation models, and then how to conduct a basic mathematical analysis of these models. I will then point out through an example that computing R0 is not the only thing, that there are limitations as to what R0 can tell you about some of the models. I'll spend a little time discussing problems that I think are specific to metapopulations, and then talk a little bit about global asymptotic stability considerations, just to show again that it's possible to do it, with always the caveat that I discussed before, that you have to know whether you want to do it or not. So first of all, formulating models. So there's a bunch of papers. I'll sort of, as a disclaimer, metapopulation models is one of the topics I've been the most involved in since the beginning of my career in mathematical epidemiology, and therefore there's quite a bunch of stuff that I've done on this, and I hope to manage to stay on the short side of things, because I could go on and on forever. First of all, how do you formulate a metapopulation model? So I have two sizes of my appearance and things. I have to remember to switch between them and etc. So if you remember the discussion I had in the third lecture about group properties and spatial spread, one of the things I was highlighting is the fact that if you think about how things are happening nowadays, more and more you can think of the processes of spatial spread as being somehow jurisdiction based, okay, where jurisdiction can be any level. It can start at the country level, or even sometimes continent level, and boil down all the way to maybe a neighborhood. But in like modern human life, you can think of most of our activities as being organized around jurisdictions in the wide sense. And so if you're thinking about the way a disease propagates between such jurisdictions, you're essentially thinking about a process that is the repetition of the steps that I have written here. So the first step, the initiation of spatial spread, is the transport of the infectious pathogen from one location to another, typically by means of being hosted upon in someone who is making this movement. Okay, so this is the transport phase. Then, if you think from the perspective of a given place, a given jurisdiction, the next step is importation. And I'm going to call importation throughout this course. When I refer to this, I'm going to call importation any event in which someone arrives in a new location while bearing the disease. So this is different from what you could call a successful, and I will call a successful importation. A successful importation, seen from the perspective of the infectious agent, is an importation event where local transmission happens. But any event in which an individual comes from another place and arrives in a new place while bearing the infection is an importation event. Okay, and then there can be success or not in that process. I'll talk perhaps a bit later about what could hinder the importation process, whether it is the forbidding of the importation itself because you're using, for instance, border control, or the lowering of the risk that someone would actually, that an importation is actually successful. Okay, but this is not the purpose here. So once an importation takes place and is successful, what can happen is that in the jurisdiction that I'm thinking about, amplification can happen. So there's all sorts of profiles that can happen, but suppose you have a chain of transmission happening locally, then at some point, this chain of transmission might result in the exportation of the infectious agent, and the loop continues. So now that exportation would result in a transport to a new location, and so on and so forth. Okay, so that's like this hopping process, if you want to think of it this way, is how a disease makes its way through space and time. Now, if you are thinking about jurisdictions, well, I mean, you can think about jurisdiction in the general sense, as I highlighted before, like it can be a jurisdiction in the proper sense, but it can also be fragmented landscapes. And so here, for instance, what I'm showing you is, this is the Toronto, New York, Detroit area. Montreal is here. And this is simply, Montreal is hidden underneath my picture, my video. This is showing you one way that we can think of space as being split into pieces. Here, this is a weighted Voronoi diagram that is centered at each of the airports in this area. And the size of the vertex, the tile, essentially depends on the volume of transport in the airport. Okay, so this is another way that you can think of space as being cut into pieces. This is not a proper jurisdiction in the sort of juridical sense, but it is one way to think of space. And what I'm going to be talking about are models that describe this situation, or the situation where you're looking at cities or countries, etc. So space is somehow transformed into a discrete entity. And so the idea that I'm going to be playing with, so I should put myself here. So the idea is that we're going to be considering a set of locations, geographical locations, or jurisdictional locations, and we're going to call these locations patches. And there's a set curly P of these patches, and they represent the spatial domain on which you're working, which I repeat is not a continuous domain. It's a spatial domain that has been segmented into subdomains. So these patches can be cities, regions, countries, neighborhoods, whatever. Patches form vertices in a graph in the mathematical sense of the term. Okay, and each patch contains compartments. these compartments are, in the sense of what I was saying before in earlier lectures, compartmental models. So, for instance, an SIR model would have susceptible, infectious, and recovered or removed compartments, whereas like an SLIRS model would have susceptible, latent, infectious, and removed. There can also be different species affected by the disease. So we think of those compartments as being very, very generic. Okay, it's anything that is in the spatial location and that we want to model. And then if we continue this reasoning, what we're then saying is that compartments, and this is a sort of way of saying which is not exactly correct, compartments may move between patches. And by that I mean individuals in the different compartments can move between the patches. And we're going to denote MCQP, the rate of movement for individuals from compartment C from patch P to patch Q not equal to P. And so I'll draw your attention here to the fact that we are putting the indices of movement from to. Okay, so things are not in the direction to from, as you could expect. They're in the direction from to. And movement, as far as this model is, I mean, the type of model that I will be presenting here, movement is instantaneous and there is no depth during movement. I'll point out that like more evolved models are going to relax this hypothesis. But here we're going to assume that movement takes place right away, and that because it's instantaneous, there's no depth during movement, there's nothing happening during movement. It simply is the relocation of an individual from one place to another. So that means that for every single compartment, I have a digraph that I'm going to call G superscript C that has arcs in some set A superscript C that describes the movement of individuals from compartment C between the different patches. Okay, and there's going to be an arc in AC from P to Q if the rate of movement is positive from P to Q, and otherwise, if the rate of movement is zero, there won't be an arc. Okay, and if you think about it, between any two locations, I can have cardinal of C compartments moving, and that means that between any two locations, I can have at most cardinal of C arrows. So what we are dealing with here is a multi-digraph, okay? A digraph in which each vertex, each pair of vertices is connected by a certain number of arrows, but a number of arrows that is potentially larger than one, okay? Now, let's look at the mobility model, and I don't need to change the view here. So if you have these, this collection of patches, then if I'm denoting N sub Cp, the population of compartment C in patch P at time t, okay? Remember, this is a differential equation. It involves time. If I assume that there's no birth or death, to make things easy for now, then the evolution of the numbers in NCP is driven up by inflow into the compartment, which happens at this rate, and outflow from the compartment, which happens at this rate. So let me explain this quickly. So this is the number of individuals in compartment C in patch P. And there are other patches that are connected to patch P for compartment C. And so the rate at which individuals move from all these patches into the patch that we're considering is given by, well, what's the population of those remote patches? It's NCQ for Q not equal to P. Okay, P is the patch that I'm considering. It's the patch that's, let's say, receiving or emitting that I'm currently considering. So NCQ is all the other patches. And that rate of movement is saying we're moving from patch Q to patch, this is weird, my, oh, interesting. Let me, sorry, I lost my keyboard for a while and I needed to progress through my slides. The rate of movement from patch Q to patch P, which is the patch we're interested in, is given by this. And of course, so if there is no possible movement, if there's no arrow, that number is 0. And otherwise, this gives me the rate of inflow of individuals from all the patches Q that are connected to patch P for compartment C. And this term here on the right then looks at things the other way. They're looking at that rate of movement is the rate of movement for individuals from compartment C from patch P, the patch of interest, to all the other patches that it's connected to. Okay, so I'm connecting to all the other patches except P itself. And of course, in this case, I'm not looking at what the remote population is. I'm looking at what the population of the current patch is and how people are moving out. So this differential equation describes the movement of individuals given any the absence of any other process affecting the population. Okay, if you just suppose that people are moving around, that describes this. And for simplicity, what we're going to do, we're actually going to play a little trick, which is going to be that instead of looking at Q not equal to P and Q not equal to P here, you can see that I can play a little game where if I define the rate of movement from patch P to patch P to be the negative outbound movement, so this term, sorry, not with the NCP, this term here in the negative sum here, okay, if I define that movement from P to P to be this negative quantity, then this large equation here is simply written as this single sum here. Because whenever in this sum over Q here, whenever Q equals P, I'm replacing MCPP by minus this quantity, and this is NCP. Okay, so I get this minus term here. So this is a very neat trick. The first time I saw that was in a paper of Wendy Wang and Zhaoshang Zhao. I find that it's probably done elsewhere, but this is a cool trick, I find. And it really is going to simplify our life. Now, I'm going to be illustrating the behavior of this type of system, and I'm going to do so by using always the same model, which is that model that I'm showing you here. So this is an SLIRS model, like we've already studied in a single population. I'm going to denote B of n, the birth rate, into the model. Phi is going to be the incidence. I should probably denote it some other way, but for now it's phi. There's death happening in all compartments. The average incubation period is 1 over epsilon. The average duration of the infectious period is 1 over gamma. And after potentially new time units, 1 over new time units, sorry, you may lose immunity and proceed back into the S compartment. So this is exactly the model that we've studied in lecture 2, I believe. I'll point out that once again, I'm using L rather than E, although a lot of the literature that you will see has E instead of L. But that's just my personal preference. Let me get myself out of the way here. I'm going to show you a few different models, and I'm going to explain how they differ. So this is what I'll call the cardinal of P SLIRS model. So this is the simplest model that you can think of in this context. So what I want to draw your attention to is the fact that to write a metapopulation model is not very complicated. So what I've done compared to this model that we have here is I've added indices on the state variables and on the parameters. Okay, so what you can see here is that the state variables have an index P, and parameters and functions have an index P as well. And that index is simply saying this is the parameters for patch P. And those parameters can change patch by patch. That's important because the characteristics of patches can be very different. Think about two countries, one very rich, for instance, with very good healthcare, and one much poorer with not as good a healthcare. Well, if you have a situation like this, then, for example, perhaps your rate of recovery is much better in the richer place because you have access to treatment. And I mean, that model does not involve treatment, but you can think of the rate of moving from S to I, from I to R as being representative of treatment. Okay. So I individualize state variables and parameters by using an index. And then I make the model into a metapopulation by simply adding those red terms that I've highlighted, those terms that I've highlighted in red here. And what this is these movement terms that I was just describing here, okay, applied to the different compartments. So compartment S, L, I, and R, you can see that I'm just looking at the rate of movement of individuals from patch Q to patch P. This is the patch I'm working in, okay, patch P here. And I'm looking at the rate of movement from other patches Q into patch P for susceptible individuals, latently infected individuals, infectious individuals, and recovered individuals. Okay, so those rates of movements can be different if you want to think about it. Perhaps, for instance, I could be very small. The movement for infectious individuals could be small. It varies, okay? And finally, the incidence function that describes the occurrence of new cases, I'm going to write this way. And this is a little trick here. I have a power Q to the P for patch P. And Q to the P is either 0 or 1. So if it's 0, this is mass action incidence because n to the 0 is 1. And if it's 1, then this is proportional incidence. I'll point out that it could be more complicated than this, okay? But in these models that I'm going to consider, I'm going to take this simple case. Okay, this is absolutely great. There's someone doing work in my building. I hope they finish soon. I will pause when it gets too loud in order not to have too much interference on the sound. Okay, so this incidence function, as I was saying, is here just very simple. It's either mass action or proportional incidence. And what I'm going to draw your attention to is that it involves only individuals present in patch P. So this is P. Of course, this is for all P, but in a given patch P, the incidence only involves those present in patch P. And that's going to be, I should point out, there are other types of metapopulation models where you admit longer range interactions. The type of models that I'm going to be describing here considers that infection can only happen if you're localized in the same patch. Okay, so that's the simplest model that we are going to look at. I'm sorry, I had to cut for the noise. So another type of model that we will be looking at is slightly more general, and it involves not only patches but species. So this is a multiple species model. So originally we wrote this to one of the topics that was considered was the spread of plague, the movement of individuals into areas where plague was endemic in some of the animal populations. So I'm going to add a set S of species, and so this is the cardinal of S, cardinal of P SLIRS model. So here you can see that what I'm doing is I'm adding another index. I now have an index for the patch P, but also an index for the species. All the rest is exactly the same, roughly, except so now I have two indices every time. The movement this time takes movement of susceptibles, for example, from species S from patch Q to patch P. Okay, movement of latent from species S from patch Q to patch P, and so on and so forth. So there's now 4 indices potentially in my movement terms. But apart from that, the idea is the same. And remember, I said contact can only happen within the patch, and this is what we see here. So my incidence function for species S in patch P is a sum over all species present in patch P. Okay, I'm not looking at other patches. So it's a sum of for all species present in patch P of the interaction terms between, for example, in this case, susceptibles from species S in patch P with infectious from any other, all species, including themselves, all species present in patch P. Okay, and once again, we use this little trick to say, well, is this mass action or a proportional incidence? But you can see this, okay? So this is a group model. This is very much a group model if you consider this without space. So if you just look at a single patch, there are cardinal of S groups in this model, and they all exist within the patch. I'm adding the fact that the patches are connected to one another. Okay, but the idea is the same as a typical group model. Another type of model that I'll show you here is one with what are called movers, stayers, or residency patch models. Yes, I need to get myself out of the way. Movers, stayers, or residency patch. So the idea here is a bit different, and this leads to models that are quite distinct from the ones we've seen before. The idea is that you want to keep track of where individuals come from. So if you think about the two models we've seen this far, this one and this one, let me take the simplest one to explain this. In this model, when you are in patch, say, Q, so Q not equal to P, and you move to patch P through this movement rate, you become resident in patch P. Okay, individuals who move from another patch into the current patch become residents of that patch. Here, we want to keep track of where individuals are from. So this could be due because of wanting to, for instance, keep track of who got vaccinated. So this is a model I've used with a student, for instance, where we were looking at people that were attending mass gatherings from a variety of places. And we wanted to know when they go back home, of course, they go back to what their home is, not to another random country. Okay, so here P is the index of the patch you're from, your residence patch, and Q is the index of the patch you're currently in. Again, so this is exactly the, I mean, if you think about it, it's roughly the same as the one here, except that, of course, if there's a cardinal of P patches, here I have cardinal of P squared subpopulations, because P varies from 1 to cardinal of P, Q varies from 1 to cardinal of P. Okay, so these models get big quickly. But the rest of the idea is exactly the same. I have then rates of movement from, and here you can see that this is a little bit more complicated. So these are individuals that are susceptible, for instance, that are going, that are residents of patch P, currently in patch Q, and traveling from patch K to patch Q. Okay, so this is how you read this. It's not as, well, I mean, it's not trivial. But the incidence function, again, is localized to the patch that we're considering. So the infection of individuals from patch P currently in patch Q depends on the people that are from all the other patches and currently in patch Q. Okay, so again, infection takes place in the patch of concern. Okay. I'm pointing this out because there are some interesting models where instead of considering movement the same way as this, people consider the amount of time spent in other patches. And when you do that, then you don't necessarily need to localize contact. Because of some of the data that I was using throughout my work, I tend to use this type of model more than other types of models. Okay, but there are other ways to formulate metapopulation models. So if I think, I should stay with a small thing. In general, if I think about metapopulation models, I can summarize things this way. I have uninfected compartments and infected compartments, and I'm just going to split all the compartments that are possible between uninfected and infected. And of course, so what we have is that the union of the two is all the compartments that I'm considering, and the intersection is, there's no intersection. And then a metapopulation model would take this form, okay? So for all compartments, so the susceptible, so uninfected compartments and the infected compartments, and for each patch, I have some dynamics that's internal to the patch, so that might include infection, but that might include a variety of other processes. And I have some movement terms that are describing the movement of individuals between the patches. And from a mathematical perspective, these movement terms are coupling together a variety of models. Now, this model, these models can appear a little big, but I'm going to show you how you can analyze them. So I'm going, I should say small for now. So I'm going to consider this very simple model. So the P, the cardinal of P, SLIRS, the simplest one. Okay. But I'll point out with some adaptation, what I'm going to tell you now carries through to the more complex models without much problem. Okay. You have to be careful, but it is feasible. Now, I'm going to assume that birth is constant, not per capita. Okay, so this is just a constant BP, and the rest of the model is as I've explained before. For now, I won't specify incidence. I'll just say whether it's either a mass action or proportional. And so what that gives me is a system of 4 cardinal of P equations. Now, we've seen in previous lectures how to analyze a model. And when you see 4 cardinal of P equations, you're probably thinking this is going to be complicated. But I want to draw your attention to the fact that this is not a random 4 cardinal of P equations. So just as a remark, so if I think of countries, for example, cardinal of P would be 193. So I would have almost 800 equations. Okay, so, but this is not the case. I mean, yes, it's the case. I have, let's say if I'm looking at countries, almost 800 equations, but there is a lot of structure in this model. And I pointed out in the group model lecture that the analysis of group models was very similar. And when I was showing you a few group models, I pointed out that it was a replication of a certain number of smaller number of equations. And this is very much the same here. Okay. What we have is cardinal P copies of individual units. And each of these individual units comprises 4 equations. So it's not 800 equations. It's 200 times 4 equations that are linearly coupled one to another. And moreover, this is an SLIRS model. I know what an SLIRS model does. Okay, so this is the coupling together of a bunch of equations that are the same, and the coupling is linear. So this is as good a large scale system as you can think of, essentially, because it's so many copies of a system. And one thing that I will stress, and this is the case also very much in group models when you're analyzing them, is that what you end up having to do is look at a lot of matrix analysis. Okay, so all this analysis that I'm going to show you relies quite intensely on knowing some matrix analysis. Now, I'm going to use the following notation. I'm going to write the set of square matrices with real entries as n sub n, or sometimes I could also write them as r to the n cross n. So this is a matrix. I'm going to use this notation. It's not always the one that is used everywhere. I prefer that one. Just be aware that this is what I'm saying. So I'll write that a matrix is non-negative if all its entries are non-negative, but that could be the zero matrix. I'll write that a matrix is positive in that sense, but it's not a positive matrix, okay? If it is a non-negative matrix, and there's at least one non-zero entry, okay? A lot of matrix analysis books use this notation, greater than or equal to 0, for this type of matrix. Or they use this notation and they say and m not equal to 0. I prefer this notation, and what I will use for what we call a positive matrix, for a positive matrix, I'll use this greater, strongly positive notation. Okay, so this means that the matrix has all its entries positive. And of course, we do the same for vectors. I'm going to denote sigma of m, the spectrum of a matrix, so the set of all its eigenvalues. I'm going to denote rho of m, its spectral radius. It's the maximum of the moduli of the eigenvalues. S of m will be the spectral abscissa or spectral modulus. of the matrix, and that is the maximum of the real parts of the eigenvalues. And finally, we are going to be using this quite a lot. So I did some work for quite some time. I mean, with Pauline van den Drieschen, she's a very big fan of this. So M is an M matrix. If it is a Z matrix, that's a matrix that has non-positive off-diagonal terms. And also, if you can write M as S times identity, so I will, like this will be identity, by the way. M is S times identity minus a matrix A, where A is a non-negative matrix, and S is larger than or equal to the spectral radius of that matrix A that you're using. Okay, so this is a definition. But you will see that M matrices come in very often in what follows. I should point out that if a matrix is M, then minus M is essentially a Metzler matrix. And so there you will see other contexts in which instead of speaking of M matrices, people will speak of Metzler matrices with a negative sign. Okay. Now, as we've done in the past, let's first look at the behavior of the total population. So let me see if I can go big. I still can't go big. Okay, maybe I could go a little smaller. Yes, this way I'm semi-big. Okay, so let's look at the total population. In one patch, what we find is the following. So we just, as we've done several times now, we take the total population, we take the derivative of the total population, which is of course the sum of the derivatives of the individual equations. We sum everything together, and what you see is that everything cancels out except for the birth term, the death terms, and the movement terms. So this is different from what we saw before, right? In a single population, we don't have movement. In a metapopulation, we have movement between patches, and this movement is here. So if I look at the evolution of the population of patch P, it is given by this. That is very much what we saw in an earlier example of SLIRS model, plus the sum for all the different compartments of the sum for all the different patches of the movement from Q to P for individuals of compartment X and the numbers in X. So this is much more complicated, of course, than when you have a single population. Now, we'll do this here, we'll do that again many times. I pointed out that it is useful to think in terms of linear algebra, and let's get started doing this right away. So we have these equations for each P from 1 to cardinal of P. It is best to write this in vector form. So what we are going to do is we're going to use these bold letters to indicate a vector. And that vector, so n is simply the distribution. So it's a vertical vector, okay? It's the distribution of population in each of the patches. So n1 to n cardinal p. B is going to be the vector of births. X I'm going to use generically as I did before to represent the different compartments, so S, L, I, and R. And D here and M, curly M here are going to be matrices. Okay, so these are vectors, but these are matrices. And D is a diagonal matrix that has the def rates on the diagonal, whereas NX is a special matrix that I'm going to call the movement matrix, and that is really fundamental in importance in this thing. So let's look at it. So that movement matrix has, on the main diagonal, it's got those negative outbound movement terms. Okay, so this is the movement matrix for compartment C. So C here would be S, L, I, or R. So that matrix has the movement outbound from all the different patches, okay? The sum of the outbound movement on the main diagonal. So these were these terms. Remember when I looked at the behavior of the total population, that's the term that I wrote MCPP. So these are the MCPPs on the main diagonal. And the off diagonals have movement from the other patches to whatever row you're looking at. So for here, for instance, this is movement for compartment C of individuals from patch 2 to patch 1, of individuals from patch cardinal P to patch 1. Okay, so the rows are the rate of movement into the different patches with the diagonal terms representing the rate of movement out of those different patches. Okay, so we'll meet this matrix again. This matrix has some important characteristics. So let me take any compartment. Then the following is true. First of all, 0 is an eigenvalue. Okay, and it corresponds to a left eigenvector that is the eigenvector of just ones. Then the negative of MC is a singular, of course singular because 0 is an eigenvalue, it's a singular M matrix. Furthermore, 0 is not only an eigenvalue, but it's also the spectral modulus, the spectral abscissa of the matrix. Okay, which means two things, that the spectral abscissa is an eigenvalue, and also that all eigenvalues of MC are left or left of the imaginary axis or on the imaginary axis in the case of 0. Okay? And furthermore, if that matrix is irreducible, which I'll remind you that, I am in the middle of, that matrix is irreducible. So I'll remind you from a graph point of view, irreducibility of the matrix means that the associated graph GC here is strongly connected. That means I can go from any patch to any other patch in a finite number of moves. I don't need to be able to go directly, but I need to be able to find a path from any patch P to any other patch Q. Okay. So if that's the case, then the spectral abscissa has multiplicity 1. So that means the eigenvalue 0 is multiplicity 1. It's just sitting there on the imaginary, on the origin, and it has multiplicity 1. Okay, just to point out, the fact that 0 is an eigenvalue is very easy to obtain. If you take the column sums, and this first result comes from this, if you take the column sums, you can see that those negative terms here balance the non-zero terms on each column. So if I take this sum, the sum of minus this quantity plus all those here, I get 0. So what that means is that I have 1t times 0. So 1t times mc equals 0 times mc, times 1t. So that's where the fact that the left eigenvector is a vector of ones and 0 is an eigenvalue. Okay. Now, let me look at what happens. So first of all, so I'm going back, remember, I'm going back to this equation here. Equation 7, I want to know what happens to the population in each patch. So if I look at this equation, and I suppose that I'm going to say movement rates are equal for all compartments, That means those matrices here, with me out of the way, those matrices here, they're equal whatever the value of C, okay? Okay, so if movement is equal for all compartments, I'm just going to write all of those matrices as M. Okay, I'm going to forget that they depend on X. And then what happens is that I can then factor out the M here. Okay, so I factor it out, and the sum of those vectors is simply N. Okay, because this is S1 plus L1 plus I1 plus R1, S2 plus L2 plus I2 plus R2, and so on and so forth. So this sum here is simply the vector N. So what I have is this differential equation. N prime is B. So remember, this is a matrix. This is a vector. This is a matrix. This is a matrix. So I have B minus Dn plus Mn. And if that's the case, this is a linear system. I can study it. What are the equilibria? Well, the equilibria are quite easy to find. So I'll set N prime equals to 0. This gives me this equation. And I can see that I can factor out, so I can move this to the right-hand side, say, and I can factor out the n from these two equations, and so I get d minus m, and remember d is a diagonal matrix, d minus m times n equals b. And therefore, if this matrix d minus m is invertible, I know that I have a unique equilibrium point, which is n star equals to the inverse of d minus m times the vector of births. And so, yes, is that matrix invertible? Is d minus m, or equivalently m minus d, is it invertible? Well, let me give you another result about movement matrices. So suppose I have a movement matrix and I take a diagonal matrix, any diagonal matrix for the moment. Then the following results are true. So first of all, if my diagonal matrix is actually trivial in the sense that it's just some scalar times identity, then I have this thing that we typically call a spectrum shift. Okay, so the spectral abscissa of this new matrix where I'm perturbing the diagonal, okay, because d times identity is just adding d to the diagonal of m. I'm perturbing the diagonal by d, then what I have is, remember, the spectral abscissa of m is 0, well, the spectral abscissa of m plus d times identity is d. Okay. When I add a diagonal matrix of any sort to the matrix N, I get a new the spectral abscissa of this new matrix is an eigenvalue. Okay, and it's associated to an eigenvector that is positive, non-negative, non-negative and non-zero, but it's an eigenvector, so obviously it's non-zero. And if m is irreducible, then adding d to m means that you get a spectral abscissa that has multiplicity 1, and this time is associated to a strongly positive, eigenvector. So all the entries in V are positive. Now suppose that I'm adding, and by this notation I mean, of course, so I mean the diagonal entries, okay? So I'm adding a diagonal matrix, and the diagonal entries of D, they're all positive. Then D minus M is non-singular, and its inverse is a non-negative matrix that is not 0, okay? And likewise, I mean, slightly differently, if m is irreducible, so because this is true for any m, but if m is irreducible, and that I'm adding a diagonal that is not all 0, then the matrix D minus m is irreducible and it's non-singular, and the inverse this time is strongly positive. So it's a positive matrix. Okay. So these are results that we showed in a paper with Bajeux, who's a former postdoc of mine, and Steve Kirkland, who's a colleague at the University of Manitoba. And so there's quite a lot in this paper. It might be interesting. I don't know. It could be interesting. So let's look now at, oh, this is still large. Okay. Let's look at the non-singularity of m minus d. Because remember what I said here was that we got this unique equilibrium if this quantity was, if this matrix was invertible. So let's do a spectrum shift. So I'm looking at the matrix m minus d, and by the result that I showed you here, when I do m minus d, my new spectral abscissa is minus d. So, but here, the matrix D is a diagonal matrix. And what happens is that the entries in D, of course, can be distinct. Not all the depth rates need to be equal. But if I take the minimum of those depth rates, then I know that things are shifted that much. And that gives us a constraint. So for the total population to behave well, and I'm not saying it wouldn't work in other cases, but that's a case where it will work well. So if I want things to behave well, I have to assume that all depth rates are positive, which is, I mean, you can make the depth rate positive and very, very small if need be, but you need to make it positive. So if you suppose that they are, then n minus d is non-singular, and therefore that equilibrium is unique. So we know that the total population in each patch converges to whatever row of that vector here you are looking at for the different patches, and that's what you converge to. So the total population converges in the patches regardless of what happens with the epidemiology. Okay. So what happens for the total population? So we've showed that this exists, but is it attractive? So do solutions go there? Well, if we look at the system, that linear system again, and we just write f of n the right-hand side, we see that when we take the derivative of the right-hand side, we get n minus d. Okay. So now suppose, and I say, so assume that d is non-singular, okay, then by the theorems that I showed you before, we know that the spectral abscissa is less than 0. That means that all eigenvalues are left of 0. That means that n star is attractive. And also, I can go a bit further. So that's if I don't make specific assumptions on D, except that all the depth rates are positive. But if I suppose that m is irreducible, and here I don't need all the depth rates to be positive. I just need them to be non-negative, and some of them are positive. Okay. Then in that case, I have a strongly positive equilibrium. So that means, or positive in the sense of vectors. So that means that all the population in each patch tends to a positive quantity. And that's going to be a constant sort of discussion. So if we make the assumption that all patches can access to all other patches, so that the movement matrix is irreducible, then we get much stronger properties. If we don't assume that, we'll end up in a situation where some patches might go to 0. Okay. But we know they go there. Whichever situation you put yourself in, there is still this property that things go to n star. Now, if in terms of the case where we have reducible movement, that means where the graph is not strongly connected. So the graph, there are strong components in my graph. So the movement matrix is reducible. I'll remind you that there is an analogy between a matrix being reducible and the connection graph being not strongly connected, and a matrix is irreducible if and only if the connection graph in this case is strongly connected. Suppose that I'm reducible. I'm not going to spend a long time explaining this, just to show you that all hope is not lost. If the matrix is reducible, then what you end up doing is working on each of the strongly connected components, and you can find that so I won't define this, there's minimal absorbing sets in the connection graph, and the number of these minimal absorbing sets actually determines the multiplicity of 0 as an eigenvalue. And essentially what happens is if you're in a minimal absorbing set, you go to a positive equilibrium, and if you're in a transient vertex in the sort of Markov chain point of view, then Markov chain graph point of view, then you end up at 0. Okay, this is just to show that even if you don't have these nice properties, you can still do things. Okay, so I'm not going to spend a lot of time on there. So now let me look at the not so nice case, and this is I show this because this is a sort of illustration of potential frustration at times. So remember that if I don't have movement equal for all compartments, I still have this sum over the types of compartments that is appearing in my equation for the evolution of n. And suppose, to make things simple, that movement is similar for all compartments. So that means although the matrices mx are not all equal to each other, they have the same zero non-zero patterns. Okay. Entries might be different, but if I have a zero non-zero pattern in a matrix, I have the same zero non-zero pattern for ms, ml, mi, and mr. Then I can define these numbers. So these matrices, sorry, m, the lower bound matrix, I'm going to put on the off-diagonal terms the minima for all the different movement rates, all the different compartments of the movement rates on the off-diagonal. So remember, off-diagonal are those terms that are positive in the movement matrix. And I'm going to put the maximum of the diagonal terms, which remember the diagonal is the negative quantities on the diagonal of the movement matrix. And likewise, I'm going to define the upper bound matrix M as the maximum of the off-diagonal terms and the minima of the diagonal terms. Well, when I do so, I get this. I get that n prime is actually bounded below by this lower bound matrix M and above by this upper bound matrix M. And these are linear systems. This is a differential inclusion, okay? Essentially, n prime belongs to this interval. And so every roughly 6 months, I run into this and, oh my gosh, a linear differential inclusion. I'm going to be able to solve this and get a behavior for n prime because it's bounded above by this and bounded below by this. But roughly 10 minutes after I make this realization, I come to the further realization that I'm an idiot, because those matrices that I've made, the upper and lower bound matrices, they're not movement matrices. Okay, so they don't have the nice properties of the matrices that I was describing before. And so what happens is that this lower bound can go to minus infinity, and this upper bound can go to a plus infinity. So essentially, yes, I have bounded my total population between bounds that do whatever they like. So it is not useful at all. Okay. But we can still do stuff, okay? Let's see what we can do even without supposing that movements are the same. Let's compute a disease-free equilibrium. So we do what we've been doing. So let me get myself out of the way to begin. Oh no, let me make myself smaller. That's it. To find the disease-free equilibrium, you need to assume that the infected compartments are empty. So in this case, L and I are 0 for all patches. When I do so, well, the transmission term is of course equal to 0. The incidence is equal to 0. And I end up with this system for all P's. And if I solve this, I have my disease-free equilibrium. Well, once again, if you try to do this, you're going to, it's feasible, but you're going to lose a lot of time, whereas it's very easy if you remember that linear algebra is useful. So let me take this system here and write it in vector form. So I use the same notation as before. I have my birth vector, my death diagonal matrix, my movement rate for susceptibles and my movement rate for recovered. I need to add this matrix nu. That's very much like the death matrix. It's a diagonal matrix with the rates of loss of immunity, nu i's, on the diagonal. Okay, so the notation is the same as before, except that I'm adding this vector nu, and also I'm noting that MS and MR can be distinct. So let's first look at the second equation here. Okay. So the second equation looks like so, and at the disease-free equilibrium, I must have this this equality. Of course, I factor out R, and so I get that this must be true. Okay. Well, there's going to be a unique solution, R equals 0, okay, the vector of zeros, if this matrix is invertible. Okay. Is it? Well, we've done that. Okay, so is this matrix invertible? Well, before we were considering the matrix M minus D. Here I'm looking at the matrix MR minus nu minus D. So essentially, we do as... Okay, sorry, camera worries. So we do, as we did before, we do a spectrum shift. And we see from that theorem that I gave you earlier that when we perform that shift, we actually shift the whole spectrum left. And in particular, we shift the spectral abscissa to a value that's negative. So what that means is that R equals 0 is the only solution to this, because that matrix is invertible. And the same way as we did before, we can also get from the fact that all these eigenvalues are negative that the limit of R of t is actually that equilibrium. So that means that at the disease-free equilibrium, I have L equals I equals R equals 0. And so now, at the disease-free, I can compute my equilibrium, and my equilibrium for S, and so for S, same business. So you can see, it's very much repeating what we saw before. If this matrix is invertible, then S at the equilibrium, at the disease-free equilibrium, will be given by this. We use exactly what we did before. Here I've changed the terms a little bit. So here I'm shifting things right. But remember, this is minus M. Before I was talking of M minus D. This is D minus M. So D minus M has all its eigenvalues right of the imaginary axis or equal to 0. And by shifting right by D, by minimum of the D's, then I'm making all the eigenvalues move right of the imaginary axis. Okay, so this is exactly what we have before, and so the D3 equilibrium is simply D minus ms minus 1 times b and 0, 0, 0. Okay. Now let's compute. Yes, let's compute the basic reproduction. Oops, sorry, the basic reproduction number. So I'm going to use the method of Van den Risch and Whatmore, the next generation matrix method. I'm going to define this vector. I don't even remember what Greek letter this is, and I had the same problem during the actual course, and I haven't looked it up, and I'm still puzzled. Okay, never mind. This is not a letter I use a lot, but I needed to change letters. So I'm going to look at, remember the method says, take the infected variables and perform whatever computations you need to using infected variables. So, and that's where the trick lies. It's important to order variables in a way that makes computations easy. And when we were looking at this type of models with Pauline Van den Risch at the beginning, we tried a variety of methods, and when finally we found a good way to write things, things unlocked. So in this case, it's simple, but the first models we consider were not the models like this. They were models like the residency patch models. But anyway, so ordering of the variables is important. So what we do is we list first the latent infections and then the active infections. So we write, as before, the dynamics of those variables as a vector f minus a vector v, where f is the new infections, and the new infections are coming into the latent compartments only. Okay, so these are these entries here. There's no new infection coming into I, so I have a bunch of zeros here. And the vector v, that comes with a negative sign, has all other flows in the system, in those variables. Okay, so these are the flows in the L compartments, and these are the flows with a negative sign again. These are the flows in the I compartments. Okay, and what I need to do then is to differentiate with respect to the infected variables. So when I take the derivative, the Fisher derivative, so the Jacobian matrix of f, I get this here. So derivative of the partial of the infection term in the incidence in patch 1 with respect to L1, in patch 1 with respect to L cardinal of P, in patch 1 with respect to I1 to IP. And of course, I have no infection in the I compartments, which these two blocks describe. Okay. Now, the incidence function we chose, whenever we differentiate with respect to L, it's equal, well, no, so sorry. So whenever we differentiate with respect to, so let's start with this. When we differentiate with respect to another patch, okay, so because remember, this is the partial, for example, of the incidence with respect to patch 1, to the L in patch 1, and this is with, and then the second would be with respect to patch 2, L in patch 2, patch 3, and so on and so forth. And remember what I said, whatever we do, we never have long-range interactions. So if the incidence function always involves the individuals present in the patch. So whenever the index k here is not equal to p, I know that my partials are 0. Okay, so that means that my derivative of the vector f is a block diagonal matrix with two diagonal matrices which have on the main diagonal the derivative of the incidence function with respect to the L's for the first one, and the derivative of the incidence function with respect to the I's on the second one. Okay. Now, at the disease free, and let's look at the two cases that we're considering here. If I have mass action, then the derivative with respect to L, of course, is 0. And the derivative with respect to I is beta p times sp. If I have proportional incidence, then the derivative with respect to L is 0 at the disease-free equilibrium, okay, because there's an I coming in here, so I could have a derivative here, but because L is in NP, okay, remember this. But at the disease-free, IP is 0, and therefore this term is 0, okay, and the other term is like this. So in both cases, that block here is 0. So in the end, what I have is my matrix evaluated at the disease-free is simply a block upper triangular matrix with the upper triangular block being this diagonal matrix. Okay, and that's evaluated. I should point out these functions here or here evaluated at the disease-free equilibrium. Now V, let's do it in matrix form right away. When I take the derivative of V, what ends up happening is, let me maybe go back to V. You can see that when I differentiate this and with respect to, for example, L, I get epsilon 1 plus D minus these movements. So what happens is that you get a block matrix that has diagonal of the epsilon plus D on the main diagonal, minus the movement matrix for latent, minus this diagonal matrix with the epsilon piece. And I should say, when I write diagonal of ZP, I mean diagonal of Z1 to ZP, okay. Minus this diagonal here, and diagonal of the rate of recoveries plus death minus MI as that term. And let me just point out, this is 0 because when you look at V, this top block, which ends up being the, when differentiated with respect to I, all those terms are 0. Okay, there's no I in this equation, therefore all the derivatives are 0. So that's this block of zeros on the top right here. Now this is a 2 by 2 block lower triangular matrix. It's quite easy to invert. There's a formula for that. And we get that the inverse of this matrix V is simply the inverse of the diagonal terms. Okay, they come here. And this lower non-zero block here takes this form. It's not simple, but it's a perfectly reasonable expression. Okay, so it's the inverse of this block times the diagonal here times the inverse of this block. Okay. And so when we remember, the next step is to compute the next generation matrix FV inverse and to find its dominant its spectral radius. So when we compute FV inverse, what we have is we have this block matrix with just this non-zero block, and V inverse. So here I've denoted V11 inverse and V22 inverse. These blocks here. But when you carry out this computation, you see that what you end up with is this F12 here times V inverse of the non-diagonal block. And F12 times the inverse of this block. But this is a block matrix. When I want its spectral radius, I'm just so the eigenvalues of this block matrix are those of this and this. This is of course 0, so my spectral radius will be extracted from this block matrix here. Okay, so R0 I simply define as the spectral radius of this diagonal block here. So R0 is this not very nice expression, okay, diagonal matrix of the derivatives of incidence with respect to the various infected compartments evaluated at the disease free. Okay, remember I haven't really written it here, but these are evaluated at the disease free times the inverse of this matrix, the inverse of this matrix, etc. Let me point out that this matrix that we get here can be quite a handful. Okay, when I remember what we saw before, if this matrix M is irreducible, then this is inverse positive. Okay, so strictly positive. Okay, so strongly positive. So that matrix has all its entries are non-zero. Likewise, that matrix, if M is irreducible, okay? If M is irreducible, both those matrices are full matrices. They have only positive entries. So computing the spectral radius of this product might be complicated. Numerically, it is easy. And that's the important thing. We can find this spectral radius numerically, and we know that we're going to be able to find it. Okay, there might be numerical imprecision problems, but overall, we know it's there. And because we can apply the method of Van den Riech and Whatmore, we furthermore have the fact, and I'm going to skip the checking of the hypotheses, but they work, which means that with R0 defined as this big ugly thing, then that disease free that we computed is locally asymptotically stable when that number is less than 1, and unstable when R0 is bigger than 1. Okay. Global stability, I will come back to this. Let me just point out that this is much harder than this local analysis. It's been done a lot, but there is not, as much as I can tell, a sort of generic way of doing it. I'll point out that the methods of Lee and Shuai are applicable in some cases. Remember this global stability methods that I was showing you using Kirchhoff matrix 3 theorem. So this works in some cases, but so far I'm not finding that there is something really generic that allows us to do it. Let me quickly show you that we run into interesting problems. This is a model that I worked on a few years ago, and what we were doing is we were interested in considering Winnipeg, where, oops, let me move myself out of the way. Actually, I should move myself here, because, okay, so this is where I live, this is where I live, this is the Winnipeg area, and we were interested in seeing what happens when you have a situation like it is here. So Winnipeg is essentially all the population in the area, and we were considering 3 satellite communities. So Portage-la-Prairie is here, Selkirk is here, and Steinbach is here. And these are locally the only non-zero population urban centers. Let's not say non-zero, there are other places with population, but the 3 locations that have essentially 10,000-ish people or more close to Winnipeg. So the population is very, density is very low outside of Winnipeg, but there's a very interesting thing, like those roads that you see and the thickness of the roads, the numbers that you see here, for example, there's a 12,750. This is the mean passage on driving passage on this road per day over whatever period this was considering. So there's a good monitoring of the roads outside of Winnipeg, and so we were interested in seeing if we could use this to study the propagation of diseases in such a context. And so, as I was saying, so we have, and that's when we published the paper, but now things have evolved. It's actually even now closer to 800,000. Portage la Prairie is about 90 kilometers from Winnipeg, and it's 13,000. Selkirk is much closer. It's that city that's right here or underneath me in the graph. And Steinbach is the one on the bottom right. It's midway between the other two, and the population is the largest. And we approximated the number of trips per day using sort of complicated algorithms to try to derive how many trips on average were taken per day between those locations. What we did is we looked at a model that looked something like this. So the urban center is indexed by W because it's meant to be Winnipeg. In Winnipeg, we had proportional incidence, standard incidence, and the other locations we had mass action because they're much smaller cities. And this is just an SIR model, no SIRS, and there is movement between the locations. I should point out the way the model works is that Winnipeg is center. There's no movement between any of the other locations. It's just Winnipeg to all the locations back and forth. Okay. It's called a star graph. We estimated movement rates. I'm not going to go into details. I'll just point out that, like if you want to estimate movement rates, you can refer to this slide. And what we saw, let me focus on this. What we observed is this is, without getting really into detail. So this is the sensitivity of the global R0 to variations of the individual R0s in all the locations. So this is what happens to the global R0, so the one we just computed, okay, the R0 for this. But of course we can cut off transport and compute R0 for each place in isolation. And those are what I call the R0 X's here. So when I change the R0 in Winnipeg, it essentially drives all the variation of the R0s in the entire system. When I change the R0s in Selkirk and Steinbach, I virtually have no effect on the other R0s. But when I change the R0 in Portage la Prairie, there are a few instances, not a lot, but where the change in R0 in Portage triggers a change of situation in the entire system. So this is, for instance, if you look at this one, this is the system has none of the patches with disease. And despite this, when I'm changing R0 in Portage from 0.5 to 3, there are instances where the whole system, the global R0, becomes larger than 1, whereas Winnipeg and the other two locations have R0s less than 1, okay, equal to 0.5. So Portage, which is, if you go back, is this place that is far away and has the fewest number of trips, seems to be able to do something that the other two can't. I mean, Winnipeg drives the whole system, but Portage is able to trigger things. And it took us some time to realize what was happening, but this is quite simple, actually. So if you look at what happens when you disconnect the entire system, your computation of R0 becomes, instead of having a big matrix, what you have is a block matrix where each block has the R0 computation for the individual locations. And therefore, as I have four blocks, the global R0 for the entire system is the max of all those blocks. And therefore, when I'm almost isolated, like Portage la Prairie, I'm tending towards this disconnection situation. I'm not quite there, but I'm tending towards this. Sorry, camera problem. So I'm tending towards this, and what happens is that this uncoupling means that the bifurcation in Portage la Prairie can drive the bifurcation of the whole system. And we confirmed this by thinking about, well, okay, what happens, does this have an effect? And that's why I was saying there that R0 is not the panacea, because while we observe this bifurcation triggered by Portage la Prairie, the effect on the overall system is minute. So this is what happens when I change the R0 in Portage la Prairie, and I change the movement rate between Portage la Prairie and Winnipeg. And what you can see is, so the attack rate is computed numerically, but remember, the attack rate is like the final size. So how much of an epidemic do I have? Well, in order to go over 10% attack rate in Winnipeg because of what happens in Portage la Prairie, I have to have a very high R0 in Portage la Prairie and a high rate of movement between Portage la Prairie and Winnipeg. So essentially, from a mathematical point of view, that almost isolated location is able to trigger an epidemic because it just comes almost as the max of those quantities. But the epidemic that it triggers most of the time has no impact on the overall system. Okay. Now, let me look at problems specific to metapopulations very quickly. I'll try to see that I'm at an hour and a half. I should call this quit soon. Problems specific to metapopulation. So this is, I think, a very interesting problem. It's what I've been calling inherited dynamical properties. So the idea is, if you look at what we've done so far, we had this SLIRS model that we know well, and we've coupled a number of copies of SLIRS models and observed what became of this coupled system involving all of them. Well, more generally, suppose I have a model that I know in a single population, and that I couple it using a metapopulation. What of the properties that I know in a single population can I carry on to the global coupled system? So there's some that we can do quite well. So existence and uniqueness, invariance under the flow, boundedness, this goes well. But for instance, okay, so I'm looking at somebody's paper, they've computed R0 in the location in isolation. What can I say about R0 in general? That's not easy. And as I've pointed out before, global asymptotic stability remains a problem, a completely open problem in a generic sense. I mean, let me look at another inheritance problem. So backward bifurcations that you will see in another lecture. I believe it's lecture 9. So suppose, without getting into details, suppose I have a model that it exhibits backward bifurcation when you look at an isolated model with a single patch. Okay. So I can have subthreshold equilibria. What happens if you can couple such patches? We've showed with Ducrot and Zongo that indeed, if you have a backward bifurcation as a single patch, then you can have backward bifurcation in a metapopulation system. So this is an inheritance. This is a dynamic property that's a bit more complicated than a single simple switch between behaviors. That dynamic property carries through from the individual level to the global level. The sort of converse problem to this, which I think is also very interesting, and I don't really know anything about. Well, I mean, I don't know any examples of, is what about metapopulation induced behaviors? So it's the converse problem to what the inheritance problem. So suppose I have a model that exhibits a well-known behavior. So I have an SLIRS, and I know that if R0 in the single isolated patch is less than than 1, I go to a disease-free equilibrium, and otherwise I go to an endemic equilibrium. Well, is there a situation where if I couple enough, or I couple some of those simple models, I get a behavior that does not show in the individual patches? So for instance, what about periodic solutions? So if I take a bunch of SLIRS models, I couple them together, can I observe periodic solutions in models which, if taken in isolation, do not exhibit them? I don't know much about this. Let me show you an example. So, as I said, so from a generic point of view, we don't really know. One case where we are able to say some stuff is a case of mixed equilibria. So that is, suppose I have a system of SLIRS models, for example, and I couple them together. Can I have a situation where one of the patches is at the endemic equilibrium, so there's disease there, and another patch is at a disease-free equilibrium? So can there be an equilibrium, and that's a mixed equilibrium, where I have some patches at the disease-free and some patches at an endemic equilibrium, for example? So to do that, and I'm going to skip over this quickly, we define a certain number of types of equilibria. I'm going to pass this quickly. I'll call a mixed equilibrium something like this, for instance. I have two patches, and I have one that has a positive number of susceptibles and 0 infectious and recovered, so a disease-free. And I have the other patch that's at an equilibrium, but all three compartments have positive entries. Okay, so this is mixed. This is also mixed. I could have a patch at the disease-free and a patch that has, for example, susceptibles and recovered, but no I. So this is not, this is also a disease-free, but it's not the same type of disease-free. Okay, so this is a mixed problem. What we're able to show is that if the graph of movement, let me move myself, if the graph of movement between patches is relatively well organized, and for instance movement is similar for all compartments. So remember, similar for all compartments means that we have the same zero non-zero patterns, not necessarily the same entries. Well, in that case we see that quite generically there cannot be mixed equilibria. The only way you can get mixed equilibria in many metapopulation problems is if you, for instance, if you have a bunch of SIRS models and you forbid some of the eyes from traveling, and you sort of create a graph in which there's movement of the eyes in one part, there's no movement of the eyes in another part, and there's no movement of the eyes between the two sort of subgraphs, then you can have these mixed equilibria. There's a paper of Pauline Van Mandrisch and Mahin Salmani that I could link to perhaps in there that discusses this. More generally, I've talked here about movements that are linear. As soon as you start to make things more interesting, things become more complicated. So for instance, suppose I have some dependence on the states in the movement rates. These are interesting problems. And the last thing I want to do is, do I want to do it really? Okay, let's do it. A little bit about global stability in these models. So I'm going to use the simplest PSLIRS model to begin with, and I'm going to assume incidence is proportional standard. move myself here. Okay. Then we had local asymptotic linear stability. Okay. Local asymptotic stability results can be strengthened and it can be made global. So if R0 is less than 1, and I'm not going to consider endemic equilibria here, just the disease-free. So if R0 is less than 1, then we have a disease-free of that system that's actually globally asymptotically stable. And how do you do that? Well, remember I said you can pick your incidence functions to make things work. Well, the incidence function we picked here, the proportional one, works. And why is that? Well, if you look at the incidence, you can see that you can write it this way because all the s's are less than the n's by construction. Then this means that the incidence function is always less than this. And so that means that there is a differential inequality for the L prime equation. L prime is actually less than this quantity. And you can define a linear system that has this equation as the equation for L prime. When you do so, you inherit some of the analysis that you've done for the stability of R0 tells you that this part here actually works out. I mean, in the sense that the limits of L and I go to 0 when R0 is less than 1. And then you can use the comparison theorem to show that the limits also hold true for the original system. And because L and I go to 0, that means you're in a disease-free equilibrium situation, and therefore R and R also goes to 0, as we've already seen, and S goes to N star, as we've already seen as well. So in this case, it's possible to show that the disease-free equilibrium is globally asymptotically stable. There's another case, I will skip over this one because it's the same idea. This one is a bit more interesting. You might want to take a look at it. It's in the S species and P patches situation. It's a bit different. I mean, it uses asymptotically autonomous systems, but overall the ideas are the same as I just showed. You try to bound solutions above by something that you control, and you see that when R0 is less than 1, then that solution above goes to something that is well behaved. And I mean, the slides are there. I'm not going to go into details. Let me just conclude quickly. I mean, this is an evidence. A space is a fundamental property, and that should come also as part of the lecture 3. Okay, and you cannot really ignore space, and you should be taking it into account. One way that I've showed you is to use metapopulation models. The interesting thing with metapopulation models is that they're easy to analyze locally. Globally, it's a much more difficult problem. Their simulation is very easy, and you'll see this in the practicum lecture about this. And I will use the hammer-nail comparison. This is not the only way to look at things. I'm showing it to you here because I think it shows a good combination of linear algebra, classic analysis, etc. But there are other ways to consider the same type of problems. This is my personal little hammer, but there are many other ways to consider the same type of problems.